So we have learned logic gates, which is the simplest physical components that implements logic operators. However, computer work with more complicated sequence of bits instead of just work with one bit at a time. So we need to combine more gates together in order to produce more complicated operations, and we even combine circuits within circuit in order to perform more complicated tasks. So that's why we need to learn about circuits. So first, at its initial states, circuits are created using gates connected together. Okay, with some input, they go through some gates and they produce some output. This is at the circuit design level. However, when we let's say sell the device to other people to use, they do not need to know the details too much. Let's just say there are a lot of circuits within your computer or within a mouse like this. But when people use them, they don't need to know the details inside there. With the same idea that in circuit design, we have one more step, which is called abstraction. We abstract the circuits with one visual notation, or we graph around that with one visual notation. Okay, and we give the functional specification. What input does it take? What output does it take? Just like, just grab the mouse here. What is the input that it's gonna take for the mouse, and what is the output that it take for the mouse? You do not need to know the circuit inside it. Okay, and also it's gonna show us some timing specification. What time does it take for a signal to go from here to here, or the token to go from here to here. Okay, then this circuit can be reused, okay, in another circuit as well. So what does that mean is that we can combine multiple circuits, multiple of the different circuits together. Then we're going to grab them again we can build multiple circuits together. Then we grab them again with a new abstraction level by giving them one visual notation, hide all the details, give the functional specification and timing specification, telling what inputs they take, what output they take. And they keep doing this. You start from logic transistor, you build logic gate, then you build simpler circuit to do simple thing, then you combine more circuit to do more thing, then you keep combining and you keep abstracting, and you're gonna create more complicated circuits. Okay. Let's just emphasize this one more time. Let's say you start with transistor, which is very simplest physical component, physical material. You build logic gate, then you combine logic gate together. You create one circuit, but it looks complicated a bit. You just grab them. You grab them with one visual notation, and you hide all the details. You give the specification. What does it do? Then you keep combining such circuit together again. You do some more complicated tasks. Then, in order for people to use, you do not need to show them the detail. You just do the abstraction. You graph around that one visual notation. Then you provide the functional specification, timing specification, and we just keep doing that up until we get our computer or our phone. Let's say for this phone, we start with transistor. Okay, then they create logic gates. Then they keep grabbing them with one abstraction level. Then they keep adding. At the end, you just grab around the whole phone with one visual notation like this, and they give you the user manual of what input does it take, what output does it take. So that one is how the circuit design work. They start with specification, transistor, then abstraction level. You go all the way up. Okay. Now in circuit design, one important software that you can use in order to do this is using LogicSim, which is an emulator that helps you to physically design your circuit by dragging the menus with the gates over here, okay, and wire them together, okay, and also build the abstraction level in order to produce a new circuit and this one is a very good tool that you should use. And it's an educational tool, so it is free, and where to access it, you can access it from here. Okay. Now let's just give one circuit example. Is gonna be over here. So you're gonna have A and B as the output. It combines several the logic gates together and produce one output. And this gate is actually have this circuit has the truth table specification. It specify what input and what corresponding output it is, like this. So let's say if A and B are false, then this one is going to be true. If A and B are different, then this one is going to be false. If A and B are the same, then it's going to be true. Okay, so the Boolean algebra for this circuit can be written as this one is not A, this one is B. So you'll see this part, not A and this one is not A and B. It's going to be not A and B. Okay. And then if you end them together, this one is you end them together, then you negate it. So this one is an AND. So you end them together and then you negate it. Okay. Then for that, you're going to do another operators over here, which is not A or B. So this one is not A or B. Then the two gonna be combined with exclusive OR, so this one is here, and so on and so forth. You want to do this, you're gonna build this Boolean algebra, or this circuit is to implement this Boolean algebra operators. Okay. Now, there is a point that notes discussing over here, which you'll see that is the Boolean expression too complicated versus the diagram. You know, the Boolean expression is, I say it's too complicated, it's too difficult to observe. So the diagram looks much better, easier to consume. But another problem is the truth table familiar? You see, this truth table, is it familiar? I think yes, right? This one you'll see it is actually negated version of the exclusive OR, okay? Or it is the XNOR. Which means that this circuit is not optimal. Okay, this circuit is not optimal. Okay, so can we? That's why we'll say, can we reduce the diagram? Okay, the answer is yes, but how? Okay, let's say for this one we can reduce it in the XNOR version, as I said, and why? Based on the definitions of the truth table. So we can simply replace the whole complicated circuit over there with this simple and more efficient circuit. If it's simpler, it's cheaper, it's smaller, it's produce less heat, okay, less waste material, so it's environmental friendly. Okay, so now it can be written in very simple form: y equal to a x nor b. Okay, so that's the point. This is much better and simpler design. Then how can we know, or how can we do this simplification? Okay, that one is what we should learn in the future lecture. Okay, now here is one exercise for you to try out, and given this circuit, okay, can you provide the Boolean expression for the functional specification, compute the truth table for the functional specification as well, and it possibly, I think I didn't add this, is possibly please reduce or simplify this Boolean equation if you know how to. Okay, but that one is a part that you should learn next time. Okay, now, so you'll see that there are different versions of the same circuits, but we need to be able to optimize. One may be better than another to build. Then how do we do that? So in the next part, we want to learn how to convert the user specification into Boolean algebra in order to perform optimization.